Okay, so last time we looked at how to basically generate a scatter plot and a line of best fit if it was linear. Now we're going to focus on nonlinear correlations. Okay, and of course we know that relationships aren't always linear relationships. They can be, curved, or they can have no relationship. They can even be sinusoidal and periodic. So we learned about all those last year in grade 11, whether we took grade 11 functions or grade 11 functions and relationships. But either way, whether it was 11M or 11U, we learned about all the different functions and quite a few of those. Now what we're going to do is we're going to find out that scatter plots can take on those same overall patterns, and of course a line of best fit could take on those as well. So what we're going to do is we're going to look at some of the statistics associated with calculations that relate to and determining the best or the best relationship of best fit, because of course if it's a linear, it's a linear. If it fits to a linear, it's y equals mx plus b, but of course we have other possibilities that can exist. So now not only do we have to pick the best fit line, which we can derive with a regression, but we also want to pick the best type of relationship, whether it be quadratic or cubic or maybe reciprocal or sinusoidal or whatever it may be. We're going to do a few of those. So day 3 again is nonlinear correlation. Okay, so we're going to look at nonlinear relationships. So nonlinear regression or nonlinear correlations are really regressions, are basically finding lines of best fit that are not straight lines. Okay, and so we kind of have to have a technique that goes along with each. We have a technique that goes along with linear and a bunch of calculations that are associated with that. That's focused on the slope and the y-intercept from some of the values that we have. But the problem is that the methods to do it for all these different types of relationships will vary, of course, with the type of relationship. So we wanted to find a better way to do that. And simplicity just allows us to say, well, you know what, we're going to use all of Microsoft Excel's abilities to find a nonlinear correlation for us, and allow us to do it very quickly and very easily, the same way that it was where we could take Microsoft Excel and do something that would take us 10 minutes by hand, we could do in a couple of clicks using Microsoft Excel. We're going to do the same thing for nonlinear relationships and not even bother doing anything by hand, too complicated. Okay, so here are some of the dominant sort of forms. We've got exponential functions, which we learned about in grade 11. Power functions, go back to exponential functions. Exponential functions are functions where the variable is an exponent or is in the exponent expression. We use fairly simplified versions of these in grade 11. Depending on your teaching, you may have gone a little bit crazier with it, but otherwise fairly simplified versions of that with a base and a constant multiplier that expanded things vertically. And then we probably just dealt with a vertical transformation factor, a horizontal transformation factor along with that. Well, we're going to use any possibility, every possibility that we will use. We'll also, with the exponential function, introduce a new base, the base 2.71 or e. Okay, which is it's kind of like a pi. That's another sort of number that's really important. But either way, there's also the power function. The power function is different from the exponential function in that the variable is actually the base for the exponent. So the exponent is the same. It stays consistent, but the base changes. So the x value, the value that changes, that you input the function and produces a value that comes out after that for the pattern in the equation, that one actually is in the base. So the x is in the base. And so we'll see that when we do that. And of course a polynomial function, a polynomial function probably fairly well as a quadratic, but it could be a quadratic or cubic or quartic or any degree above that, although we don't tend to use degrees very far above that anyway. Okay. Take-home message is calculations for determining the curve and best fit are much more complicated than we will be doing by hand. So of course we're going to do them on the computer. Okay. For our degree of correlation or a correlation value or score, I guess, as it were, we use something called r squared, the coefficient of determination. And that is literally, for a linear relationship, the square root of r squared gives you your r value that we know and love by this point. Okay, r squared is always between 0 and 1. That makes sense. If r value has got to be between -1 and 1, if we square it, it's got to be between 0 and 1 because it's always going to be positive. If r squared is equal to 0, then there's no correlation. If r squared is equal to 1, then it's a perfect correlation. Okay, but we don't tend to do many more explanations past that associated with it. So as far as the theory involved in this, the basic theory is as follows. For nonlinear data, what we do is we look at our model equation, whatever we think the type of relationship is. And what's going to happen is this. There's natural variability in y. Variability exists. Variability exists because of measurements. Variability exists because of populations or measurements. Variability exists. Okay? The variability could be caused by two things. Just by simple variability. Okay? Just by, people are different. There's no clear relationship. It's not always perfect. Not all lines will transcribe every single dot or every single data value that we have, or in this case, data point that we have between x and y. But what will happen is there will be natural variability. But there will also be variability that's caused by the function. In other words, the function will increase or decrease, and it'll increase or decrease by a specific amount because of the fact that it's quadratic, or because it's exponential, or whatever. So there's two ways in which y can vary. What r squared looks at is the amount of variability that's caused by y changing with x, or in other words, by the function. Okay, so we have this thing called y estimate, which is actually the function. Okay, and so when we look at our r squared value, it's a fraction, numerator divided by denominator. Here's my numerator, here's my denominator. The numerator is the variation in y that can actually be explained by my function. Put in x, you get a change in y. X and y relate. Okay, the bigger this is, of course, the better. All right. The total variation in y could be caused by two things. One, it could be caused by x changing, and of course y would change along with x. That's a good fit for the relationship. And then, of course, there's natural variability that could exist that doesn't have to be caused by a change in x. Okay, or that's independent of our equation. Okay, and that's the total variation in y. So if we look at the total variation in y explained by my equation, or by my relationship on the top, and the total variation in y in general, including the variation caused by x, and then the variation that's not caused by x, then we get the r squared value. Okay? So, that's sort of the whole idea. And if I have a quick peek at this diagram, and you'll see from there. Okay? As we move on, okay? The results, of course, depend on the relationship that you pick. Obviously, you want to pick the relationship that matches it the best. Okay? And obviously, the r value will change if you pick a linear versus a exponential versus a quadratic versus a sinusoidal or whatever. Okay? So anyway, when you're determining the most accurate curve of best fit, we look for two things. First of all, we look at the r squared value. Okay, that's key. I know I have put that second. But the r squared value, the higher it is, the closer it is to 1, the better the fit is. If I have one that's an r squared value of 0.7 and an r squared value of 0.9, I'm going to pick the r squared value of 0.9 for, I don't know, let's say that's for quadratic. And then for exponential, it's 0.7. Well, of course, I'm going to pick quadratic because the r squared is 0.9. But there's another factor. Now, the book talks about it being the extreme data values, the lowest and the highest data values. How good is my equation at predicting the lowest and the highest data values? That adds inferences or ideas to be able to extrapolate your curve, okay, to both the smaller values and higher values of x. But I like to actually do it for all values. Okay, the better that your curve is at actually predicting the real y value that you got with your measurement, assuming it's accurate, then of course that's going to be the better fit that exists. So that's sort of the theory behind the notes. What I'm going to do afterwards, of course, is talk a bit more about how to actually do this in Microsoft Excel and how to use the benefits of Microsoft Excel to actually make these comparisons and choose our best curve of best fit.